Hey folks, how's it going? How's it going? I'm getting set up. Hope everyone's doing great. I'm configuring things, putting things in the right place. I think I'm compiling things right now too. Yeah. We might have to hold off because I'm in the middle of compiling something that I haven't optimized yet. It's like I haven't optimized the compilation time of it yet. So it's going to take a little time to compile. But that gives me time to set things up. Setting things up. So today, oh man, today we are done implementing Jank's IR. The custom IR that we've been building out, we have done. And the whole test suite that Jank has, the 800 whatever tests in the functional testing suite, and then the whole end-to-end testing suite, and all of our unit tests, everything passes when we run through when we push all of our code gen first from our AST into our custom IR and then into our brand new code gen that we wrote. We've done it. They said we shouldn't do it. And we did anyway. Made it happen. So today we're going to use some of that, and we're going to focus on taking a couple of, well, we'll see where we get, but we're gonna take some benchmarks, and we'll start with some really small ones, micro benchmarks they call them, and we're just gonna do some profiling. So we're gonna figure out where Jank is slow right now, and there's going to be a ton of low-hanging fruit. So like, yeah, I just spent 4 weeks. Today marks 4 weeks, and today is when we get the pull request open with the CI passing. So we have 4 weeks to implement, design and implement a custom IR, and then code gen from that IR as well. But we spent all that time on this IR, but that doesn't necessarily mean that that's like all the optimizations we're going to be doing are going to be using the IR. It's just that I knew I wanted to have that in place, and I know that there are some optimizations I want to do that are going to use that. But there are also optimizations that we're going to do that are just going to be in the runtime. There are other optimizations we're going to do that are going to be in code gen. There are going to be optimizations we're going to do that are going to be done in the AST when we're analyzing. Yeah, we have optimizations to do pretty much everywhere except for lexing and parsing, because those are for our purposes right now, those are fast enough. I don't think those are going to be showing up as a problem compared to all the other shit that we're going to be doing. But in order to jump into that, first thing we're going to do is we're just going to grab our first micro benchmark. You know, maybe we should actually start a doc. Maybe we should start a doc. So what is it? We are in Q2 of 2026. So what I want is this guy, but 2026 Q2. And so yeah, I've been doing all of the IR notes elsewhere, and so we don't actually have all of those here, but that's fine because I have a lot of information on that in another doc. But this really helps when I write my blog posts, especially the optimization related blog posts where it's like, oh, we start with this thing, it takes this long, I do this thing, and then this is the effect on that, and then I do this thing, and then that's the effect on that. Like, and then I create charts, bar charts of the performance as it changes relative to how it started and relative to Clojure JVM. It's really hard to do that if you don't actually just keep track of all of the numbers. You really got to write those things down. So we're going to do that. The other stuff that we're going to write down, though, is we're going to write down the optimizations that we're going to want to do. Do. I think my throat tickled. So we're going to have a couple of benchmarks we're going to start with. The first one is just going to be Fibonacci. And so I have a recursive fib. Where is that? Yeah. I have a recursive fib right here. And this is not written to be fast. It's just written to be, as straight up simple as it possibly can be. And we just want to make it as fast as we can using the compiler and the runtime. Now, of course, if somebody wanted to write a faster Fibonacci in Clojure, then they absolutely could. And if you wanted to write the fastest Fibonacci in jank, then you would not even use like a Clojure function, like a CPP defin, or you wouldn't use a defin, you'd use a CPP defin to define a C++ function. And then you wouldn't need to deal with any of the boxing, anything like that. But we're going to take this as it is and then just see what we can do to optimize it. Because I know that this particular micro benchmark, compared to Babashka, compared to Clojure JVM, compared to Python, jank's really slow at it. And we're going to see why. There are going to be a bunch of like really obvious things that we can do in order to speed that up. And let's see. The other benchmark we're going to be dealing with for sure is the ray tracer. And this is an old one that it's actually a couple years old at this point. If we were to jump into the jank blog, I think we're going to see. Yeah, so we have optimizing ray tracer right here in 2023, April, actually. So 3 years ago, I wrote this ray tracer in Clojure. And this is just porting from a really fun tutorial. And this was, god damn, so much has changed in jank since then. But spoilers, at the end of this article, so we started, jank was taking 800 milliseconds. If I remember correctly, this was actually done before jank was even using a garbage collector. I believe it was in this blog post that we end up adding BOEM-GC. Let's see. So yeah, jank was taking 800 milliseconds, and Clojure, what was Clojure taking? 69 milliseconds. Nice. And then changes, compiler flags, changes. And then, okay, so we were using the GC in incremental mode. Okay, so we were already using the GC. I think we were pretty new to the GC at this point, though. and we were able to actually get down to 69 even, which technically beat Closure's result by less than half a millisecond, but basically put us in, you know, in the same territory. So where we're at now is that when I run, actually we should remeasure to get like what Closure reports at now on this machine, because my machine has changed in the last 3 years. But then we're also going to want to, you know, do the same thing. So we're going to want to see where jank is to start with, and then we're going to profile the shit out of this, and we're going to try to get jank to be faster than Closure, or at least as fast as Closure. So we'll do a revisit of this ray tracer. I think it's a really great example or a really great benchmark, because it's a lot more practical. Like it's a lot of like typical Closure. That's a lot of just maps and numbers, really. And so it's a good benchmark for maps, which we use all the fucking time, and a good benchmark for number crunching, which computers do all the time. So let's maybe start with grabbing some numbers that Closure. Like, we're gonna want some numbers for fib. We're gonna want some numbers for the ray tracer that we're gonna start with. So I don't know how to do. Maybe I'll just do like CLJ. No, we're gonna want to do a proper benchmark. So defen. Okay, so we could just do, I think that Closure has like a load file, right? What's the doc for load file? Load file takes a name, sequentially read, blah, 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 blah. Okay. Can I just do fib.jank? Cool. So it's a .jank file, but it just contains Closure code. So Closure's going to load it just fine. Closure doesn't really care about the extension. And then the other thing is, if we do a require of, not the decompiler, this one. And then if we just do a quick bench, let's do fib. I don't know how long. We're gonna see how long these things take. So like, what does fib 40 take? Oh, it's called Fibonacci. What does fib 40 take? And of course, the first one we're just gonna. Okay, so maybe 40 is too much. Okay, maybe 40 is too much. Wait, why can't I Control C this? Okay, yeah, 40 is too much. I'm gonna do 20. Oh, that's super fast. 30? Yeah, let's do 30. So we'll do a quick bench of Fibonacci 30. And then let's get this into our, okay, so we're doing Fibonacci 30, and so we should check here also the version. So yeah, 21 and 112.2. Because whenever you do any sort of benchmark shit, undoubtedly people are going to be like, oh, what version, JDK version, and blah, blah, blah. So we get 269 and 276. I'll just do this 3 times. So I'll take all 3 because it's already doing it. I mean, it's already, Criterium's already doing it a whole fuck ton of times and giving us the mean. This is actually going up, which is fascinating. Not what you would generally expect. I'm just sort of curious, if I do this again, is it going to be like 84, 284? What if I'm right? No. Okay, it goes back down. All right. So yeah, we got the 3. AD309. Hope you're doing great. Welcome to the stream. Okay, so this is for fib, and then we're going to do the same thing with ray. We have, so outside of this, we actually have a ray. I think it was called CLJ ray. I swear. Yeah. Okay, so we have a line again project for this. We do a native image, blah, 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 blah. And then inside of source core, we have, we'll just have a main function. Okay. So I think we just want to do a line REPL in here and then bring in Criterium again. Where was this? It's this, and then we'll just do, so I think I can just do main like this. I just want to run that and make sure. Yes. So we'll do a quick bench of this. And then while that's running, so COJ ray core, I just want to make sure there are some parameters that we run with. The aspect ratio, image width, samples, focus distance, aperture. I kind of want to capture all of these to make sure that they're going to be the same in both. Let me just grab all of these. So I'm going to bring, how do I want to do this? I'll probably want to just do one of these and then one of those. And then I am going to delete any comments here and then just bring that like so. I'll just leave those as is. That gives me everything I need. Now, okay. So this is 82.7 on this one. Closure JVM, and again the JVM details. We'll check again after I restart this. Hey Davros. No. So I was going to ask if this closure inspired language could infer vector as fixed length small vectors, but I see vec3 create function, so I presume you're doing strong typing going on for that. No. So vec3 in this case is not a vector. It's annoying naming here, but this is a vector in the case of like XYZ RGB. This is a map of 3 things. So we're not using positional data, we're using associative data. And so sure, like we could represent XYZ as positional data in a closure vector. But instead we're representing it as RGB inside of a closure map. Could be XYZ inside of a closure map. But either way, we're using maps instead of vector data structures. But these are, in terms of linear algebra, these are three-dimensional vectors. Correct. So it's a map of XYZ. Exactly. And so we can see that here, right? Vec3 create takes in RGB and it gives you a map of RGB. So this is, jank is not a closure inspired language. Jank is closure. Jank is a closure dialect. And so this is, everything here is closure. Everything here is closure. Okay, so we're gonna run this guy again. And so what this is outputting right now is that each run actually outputs the color data for the image that it generates. And right now we're generating a really small image, which allows us to do this pretty quickly because I wanted the benchmark to be, pretty small. And that's why the image data is actually, it starts right here at P3. It's just this, and then it ends in meow because that doesn't need to be part of the image, but it is allowed to be. So I'll do one more of these. Cool. So we are looking at, 82 to 90. And then we're going to have to see where jank lies with all of this. And no doubt jank is going to be significantly higher for both of these right now, because today's the first day that we're jumping into optimizing jank. And I mean, the past 4 weeks have been laying the groundwork to be able to optimize jank by creating the custom IR, but we didn't actually do any optimizations. In fact, I think probably the move to the custom IR removed some of the hacks that we had in our old code gen, and so jank probably slowed down from that. But that's fine because those were hacks in the code gen to make things a little faster. We're gonna like the optimizations that we're gonna do here are gonna be more longer term, better designed optimizations. Okay, so let me see. Now, unfortunately, the thing that I was looking at is still baking. Still baking this. How long is this gonna be, I wonder? And is there a better way? Can't be that long. I'm gonna leave it. I think I'll give it like 5 more minutes. Cool. So now there's another benchmark that I need to remember the name of. Where is it? Yes. So there's a benchmark for ASCO router, which sounds like I'm not saying English, and that's because I don't think I am. ASCO router benchmark. What? Wait, no, this isn't right. It is right. I thought this was on GitHub, but it's not. It's just this, it's on this other thing that looks a lot like fucking GitHub. Like this whole layout is I don't know what this NMM site is, but this is basically a GitHub knockoff. Have there been any game experiments with jank already? Something with Raylib? For sure. Yeah. We had somebody do a small demo. We had somebody do a small demo with Raylib. We have somebody who's working on a game engine in jank in OpenGL. And then we've had some other folks using jank with SDL. And I don't know what graphics backend. And also we had a pretty neat, like immediate mode GUI demo with OpenGL where this was done by Kyle C., the guy who originally wrote jank's nREPL server. And so he was demoing building immediate mode graphics with the nREPL server. And so he was interactively building the like a GUI application using the jank REPL, which is fucking awesome. Anyway, so this router thing has a benchmark that is very easy to run and has jank here. So jank currently ranks slower. Well, it ranks about where Babashka is. Sometimes faster, like in this one. Sometimes slower, like in these. Oh, this is slower. This is slower. I guess. Oh, this is faster. Generally looks like it's slower. This is faster. Yeah, I'd say that's like 2/3 of the time slower than Babashka, which is not great. So we're gonna do better there. And then like Clojure JVM, on the other hand, is like way, like this is an order of magnitude faster. This is several times faster, Yeah, so we will, we're gonna see what we can do. Oh, hey, I borrow check. BT Dubs, thanks for the raid. I hope you had a great stream. I hope you're doing lovely. I raid you, by the way. I love it. I love it. We're doing all right. Full caps. I'm glad to hear that. Welcome, everyone. Welcome, everyone. We are just looking at, we're looking at benchmarks in, Clojure and jank. And we're going to see what we can do. We're going to do some profiling. We're going to do some benchmarking. And hopefully we're going to do some optimizing. Did bits of the Lang website and added Musi for C++ developers bit. Hint, hint, your kind of people. I will take a look. I'm going to have to take a look. Why don't you drop a link? I borrow check, by the way. You are welcome to. There you go. Everyone, take a look. It's actually easier for me to type that. The Musi programming language. Expression first programming language with pattern matching. Effects, small command surface. And we're looking the bottom section for language. Hold on, you got a lot of stuff going on here. I think it's the first time I've seen this this site, so I'm gonna take a look. I like this logo, lips. I like this style as well, but I actually don't know. Okay, so yeah, this isn't my normal browser, so I don't have Dark Reader enabled. This is actually your style. I like the style of the code that you have here as well. Two command lanes. Use Musi for package work and music for direct source or artifact work. I don't actually know what that means. Four items, 5 items. It's interesting that you're specifying the items that you have here. These are, I imagine, like the sort of sections that are, or no, not, I guess you're using the term section here. So those are the, I don't know, subsections of that section. Is that right? If I click on this, does it have subsections? Yeah, chapters. Interesting. Music is like Java C. Ah, Musi C. Fuck. Okay, now that I know, that's clever. But that was, but it was maybe too clever for me because it wasn't clear at first. But now that I see it, I'm like, okay. I would also do that. So I would also do that if I had the opportunity to take advantage of that sort of wordplay. Open section. Music for developers. Translate familiar habits into Musi without caring over syntax that does not fit. Language guides. So this is what you were working on, C and C++ here. Let's see, translate C23. I mean, I have no idea what C23, like I haven't caught up with what C does these days, you know? Like I'm pretty hooked into the C++ side of things, but I hope that the C folks are getting good stuff as well. It always seemed kind of like ironic, I don't know, to me, because C as a language is philosophically so minimalistic and conservative, traditional, that like, I don't know. I've seen people who, like C devs, who I think reject the notion of doing anything like from this millennium in C, you know, they're only writing like old style C. So we'll, whoa, holy raid. Nathan Bags. Thank you for that, raid. I hope you had a lovely stream. I hope your stream was tremendous. That is a hell of a raid. I appreciate you. Everyone, welcome. Well met. Well met, traveler. Have a look at my wares. I used to be an adventurer like you till I took an arrow to the knee. You just caught us looking at the docs for the Musi Lang, and we're trying to figure this out right now. Obligatory apology, as I suspect LOVM IR is abound. Oh, you know, interestingly, we've for the past 4 weeks we've been working on a custom IR for the jank programming language, and it's not LOVM IR, but maybe this Musi Lang, which is what we're looking at right now, is that. I keep interrupting myself in the middle of reading these sentences. So we're going to find out. Does not have LOVM, says Eyebrow Checker, who's the author of Musi Lang. Yeah, C99, Davros, that's what I was talking about. Like, I feel like a lot of C devs I see are just kind of what C standards, there's got to be like so there's C89, C90, 94, 90. Wow, okay, so C was doing shit when C++ was not. Right? Because C++ was like, okay, here's C++ 98 was the first standard. Although C++ existed before that. And then 03 and then nothing until C++ 11, right? But yeah, don't a lot of people, am I like, I know I'm on IRC, and so kind of have that old soul. But I feel like I get the impression that a lot of people still just want to write C89. And I don't actually see people like, oh, I'm using C23. I'm taking advantage of the coolest features that C has to offer. What is C like? What is C? What? Yeah, IRC. It's in the name. Zing, zing. You are right. C11, blah, 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 ratified Unicode. Okay. Type generic expressions with a underscore generic. That's an ugly fucking keyword. But sure. And a cross-platform multi-threading API. Interesting. So C folks actually have a cross-platform multi-threading API. They don't actually just have to use pthreads and whatever like platform-specific shit. Fascinating. Productivity, Nick Pangburn. Welcome. I appreciate you. C17. Rather than introducing features. Okay, so this is your bug fix release, and then 23, which is the current standard. Man, this doesn't even list like any cool shit that we got. Where's the cool shit? Null pointer. Fascinating. C has null pointer. Wait. Man, what does that do to null? Because null, like the fully uppercase null, has been a C thing for so... Like, there must be so many assumptions that are made around, like... I guess no more than C++. I guess no more than C++, and C++ did the same thing. Yeah. Okay. So a lot of this stuff, like C++ did this, C++ did this, WB and UWB, interesting. Underlying type of an enum, love that. C++ did that as well. True and false keywords, what? Yeah, so there must be C folks who are like just fucking going bonkers over this shit, right? Because I was on IRC, what do you know? And I was chatting with one of these C89 folks, and they were shitting on me and C++ for having like bools and converting things to bools and now joke's on them, C23 has true and false. Wow. Okay. Anyway, we're this is such a tangent. We're in the tangent of a tangent right now. But that is cool to see. Variadic functions no longer need blah, 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 zero initialization with uniform style initialization, right? So they don't call it uniform initialization here, but this is uniform initialization from C++, right? Interesting. Coming back from Rust, I'm more like, how can you not have true bool? Yeah. Herons, got to jump. Good luck with the rest stream. Hey, thank you. Thank you. Have a good one. Hope you're doing, hope you have a great day or night or whatevs. And if I never see you again, wait, what was the Truman Show line? what was that Truman Show line? Preprocessor, C++ compatibility. Attributes, this is nice. U8 prefix, sure. Okay. All right, we're done with C. We were looking at this Musi lang. Is it Musi or Musi? Is it like a Z or like a S? I think it, or like Musi. Yeah, I don't know. Should I be putting on my Spanish accent? Does not matter. Fair. Habits that transfer well. Habits to translate. Match. Well, I mean, yeah, having match blocks in the first place is great. All these UK time zone peeps, it's 11 p.m. Yeah. All right. That is great. That is great eyebrow check. By the way, I need to look more into Musilang in order to get an idea of it. But from glancing, I like that it's expression first. I like that it has pattern matching. We'll have to see about the effects. But it feels a little rusty. And that's cool. I dig that. And you have a really well built out website and documentation page, and I dig that as well. Was this all coded like and designed by hand, or did you use AI for this? Be honest with me. IBC, BT dubs. Because if you build this all out by hand, AI, okay. I was gonna say, if you build this all out by hand, that's like, I mean, props to you. But these days, it's hard to believe, you know. The person Harans had also made language psych on GitHub. Oh no shit. The original was all non-AI. Yeah. I mean, I get people these days. I get people who are coming at me with like libraries for jank and proposals and stuff like that. And they've built this whole fucking thing, and it's like, oh yeah, I just built this thing this weekend, and it's like 50,000 lines of code, you know, and they're like, maybe you can integrate it in jank. I'm like, well, that's cool. You built something really cool, but like how can you have any confidence in this thing? Let alone me have it's like not even old enough to like, you know, wipe its ass. You know, it's not even old enough to be like left without, you know, supervision. It might choke on its own spittle. But there are some things like, you know, building out a website, which you don't really need to. You're not doing security sensitive shit. You know, you just sort of like putting a bunch of stuff together on a website. Makes sense. Fresh and still dripping. No, you don't need to leave. That's good. The ability to rapidly generate large volumes of code, definitely double-edged sword. Absolutely. Yeah, I mean, somebody had just proposed a Go style concurrency library for jank, which is super cool. They're like, oh well, we want to be able to do like Go style concurrency in jank, and jank is a native Clojure dialect. And I'm like, that's awesome. You know, I like, let's see the benchmarks against Boost Asio. Let's see the benchmarks against Go. Let's see the benchmarks against Core Async, and maybe Rust's Rust Async as well, to get an idea of where it stands. And then I don't know, a couple weeks later, they had those benchmarks as well, which I'm sure were also vibe coded, and it's cool. But like, I don't know as a maintainer, like how, where's the point where like something's now battle tested enough or you have confidence enough to actually bring it in. If it's a third party library, great. Like, yeah, now people can use this. If anybody wants to try this, they can. But if it's something that actually needs to be integrated into the language runtime or something like that, then yeah, harder sell, much harder sell. I can't believe we used to type every character. Yeah, I still do, man. Like in Jank, I still type basically everything. I think I'm gonna be a tough one to convert to the, like, I mean, the thing is, like, why do we code? Why do we code in the first place? I suppose that's a good question. A lot of, like, when people code for work, right? They're coding in order to create a product. They're coding in order to generate value for the company. They're coding in order to solve problems for a customer, everything like that, right? And I get that. If you want to use AI to help you do that, be more effective doing that, then for sure, like you're creating more value as an employee, and that is what employees should do. And companies should seek high value employees. But on the other hand, some of us, and in the open source world, a lot of us, we write code because it's one of our favorite things to do. And so for me, like, I like the whole typing out thing, you know. I like the process of typing out the code as I build software. For me, there's a craft to the way that code is designed. And it's lower level than just the architecture of it all. And yeah, there's, you know, you say flow state, like, I love that feeling of just writing the code. And I wouldn't pay someone else to do that. I wouldn't even, here, let me put it this way. If somebody said, hey, Jay, let me pay you so that I can write your code instead, depending on the amount, but like, unless it's a crazy amount, I would just be like, nah, I'm good. I want to write the code. That's what I'm fucking doing here. I quit my job so that I could work on my programming language full time, because this is what I want to do. I don't want an AI to do it for me. I don't want you to do it for me. I want to do it. It's fucking fun. It's fun. All right. So we're back. We're back. We were looking at benchmarks. What was the other benchmark we were going to do? It was this router thing, and I don't actually know what the contents of this benchmark is. Can we look? Can we look at what this benchmark is? So this, I don't want to click there. I want to click here. And so apparently to run this benchmark, all you need to do is run this jank benchmark, blah, 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 blah. So there's a bench directory. Cool. So yeah, there's actually already some jank shit in here. Jank shit. I see. So this is, we already, I guess we don't have the closure versions of this benchmark, but we still could. Oh, should I allow the the post from eyebrow check, by the way, because it says fugly? Yes, you can say fugly in here. That's fine. Yeah, I'm not going to worry about this one right now. what I will say is, before we jump too much into the weeds, for those of you who've come in recently through the raid, and you're wondering what the fuck it is we're doing, I just wanted to give you an idea. So we're working on the programming language called jank, and jank is a native Clojure dialect. So it's Clojure's a form of Lisp. It's kind of like a modern Lisp, and jank is a dialect of Clojure that is on LLVM, and jank has a couple of very unique. Jank has a couple of things that make it very unique. So the first thing is it's a Clojure dialect that's native, that's on LLVM. And the second thing that makes jank very unique is that it's not just a Clojure dialect, it's also a C++ dialect. And that sounds probably pretty weird, and that's because it is weird. It's quite unprecedented. And what this also means is that, like, when you combine those two, you have a language that it's a dialect of, on the one hand, a super dynamically typed, polymorphic, garbage collected language. But then on the other hand, it's also a dialect of C++, which is like a low level, or at least, these days, relatively low level systems programming language that's statically typed, does not have a GC, uses RAII. And jank is both of these. And that's the appeal. The idea is that you can, so my background is in game dev, instead of writing your game engine in something like C++ and then also having a scripting language like Lua or whatever, and then some sort of bridge through a C, like through the C ABI for those two, you could write your game engine, let's say in jank, using the more of the C++ side that's statically typed and is not garbage collected and everything like that, but seamlessly you can traverse this whole spectrum of the C++ side to the Clojure side, to where, in the middle of your more C++y function, you can just be calling the more Clojure-y stuff, and vice versa. And so your gameplay logic can be more dynamic, more polymorphic, and just easier to iterate on, because you're not being bogged down by nominal typing or static typing in general. It's just data. But you don't need to sacrifice the performance when you don't want to. And so, here's a quick example of Clojure style namespacing, but then just like including a C library and then grabbing out shit. Now that's C, which is not as exciting. But let's take something like C++, right? So here we'll just include boost, right? And so we can just grab this. Now, the amazing thing here is boost file system file size is a function, but it's actually an overloaded function. So there's not like one particular function that we're grabbing here. We're grabbing the whole set of overloads, and then we can actually just rename that to be file size. And so here, when we call file size, and we're giving it a C string, so this is just like a C string literal. This is then going to do proper overload resolution on the C++ function, get us back the native value that is the result of that. And then here we're passing it to a Clojure function. And so then there's going to be an implicit conversion that's going to happen between the native value and the Clojure runtime in order to convert those. Now, file size can throw an exception, and that will be the C++ value, and we can catch that C++ value directly as well. And so this is, I think, a good example of Clojure meeting C++, and just this intersection of statically typed systems programming and dynamically typed garbage collected, polymorphic application programming. That's what we're doing. So jank is, this is Clojure, but we took away the memory hog that is a JVM, and somehow C++ified it at a smaller scale. Kinda, yeah. It's pretty unique. The other thing that's worth mentioning is, if you know anything about Lisps or Clojure, then you'll know that there's this whole like idea of REPL-driven development that is built on just-in-time compilation. You have to be able to just-in-time compile code. And so jank supports all of that as well. And what that means is that you're going to be able to, and you are today, we have a JIT compiler for C++ built into the runtime. And so you can JIT compile arbitrary C++ code. That means instantiating new templates even, right? Any sort of C++ you want to do, we can JIT compile it. So if that sounds interesting, then give jank a look. In game dev legend, a low-level capable Lisp has happened before. Naughty Dog goal for sure. I mean, Naughty Dog is a pretty badass company historically, and they've a lot of their tech has been amazing. Yeah, I mean, if you look at like the first Last of Us, for example, how that game looked, what they were able to squeeze out of that on console, beautiful, beautiful. Okay, so we're gonna jump back into we're gonna do some code shit now. There's been a lot of fun talking, but we need to jump in to do some code. Let me take a look at what we have here. We still don't have any of this. So I have this thing that's been running. We're gonna need to hack. We're gonna need to do some hacking here. We're gonna need to do some hacking. Let's take a look at what we need to hack in order to get some stuff compiling. Okay, yeah, so we don't have this. Close. Let me just, actually we don't want any of these. I'm gonna hack some shit right now so we can work around some stuff. Clojure walk, that's fine. Yeah, I don't want these either. And then Clojure core. So, yeah. Okay. So let's just do this and then, yeah, that. Yeah, I don't know if Naughty Dog ever like licensed out Goal for other people to use. Probably not, because it was probably really integrated into their tech stack. And then also on top of that, they would have to find other companies that actually want to write like a low-level Lisp in order to build their own software, which is, I think back then was probably even harder to come by because functional programming hadn't picked up the way that it has these days. And I love that it has these days. a recent attempt to recreate it. You know, I have seen something on GitHub about recreating goal. I think that's and also open goal is is a pretty great name that has nice wordplay going on in there. I think that a more modern take, you know, it doesn't have to be jank, but a more modern take on a low level Lisp is probably preferable. Like in terms of practicality, is probably preferable to recreating goal. Just because that's like what, 20 years old? More? Probably 25 years old, if I had to guess. Yeah. Okay. What were we? Yeah. So we're gonna kill this. We're gonna take a look at fib first, and see what we can see. So we should have that now. Yep, we're compiling that now. So let's do a fib jank. What are these linker errors? Undefined reference to this. Yeah, that's fine. That's expected. Where are we referring to that though? And then nrepl stuff. Okay, so all that is in main. So yeah, when I hacked this, what is that? When I hacked this jank load here, all this stuff. All right. And nice. So now we wait, we shouldn't need to do anything here, right? Yeah, we shouldn't need to do anything there. Let me hack a little more. Perfect. Yeah, I just was in the middle of some stuff right before the stream that made it so that compiling in a release build is going to be a pain. And so I had to do a little bit of surgery to make that viable. But here we go. So let's do one of these. And let's take a look at the IR that we have for fib first. So I'm going to close this because we're done with that. I'm going to close this because we're done with that. We're not going to deal with this. So we're just here. Okay, so we have our fib function. A recursive fib function takes n if n is less than or equal to 1, then return n. Otherwise, we're going to recur into fib with n-1 and n-2, and we're going to return the sum of that. So we get to take a look at our jank IR, right? So this is what we've spent the last 4 weeks building out, is our custom IR for jank. And let's take a look at how this function actually looks. So we grab n, we grab 1, we grab less than, and we do a dynamic call to less than after dereferencing it. We convert that to bool using truthy. We do a branch on that. So if the branch is true, we grab n, we return it. And if it's false, then here's where we're going to do our recursion. So we have a named recursion here. So at the instruction level, jank knows that this isn't just a function to call, it's actually a named recursion, which is different from if we were to use recur, because we can't actually use recur here because we're not in tail position. Recur can only be used in tail position, but it is named recursion. And so we note that here in our IR. So we do our named recursion here, we do our named recursion here, and then we grab plus, we add these guys together, and then we return that. Eyebrow check, by the way. Friend called VCU, look here. All good, man. Thanks for hanging out. I hope you have a good one. So this looks reasonable. Looks like we have some stuff here that we could potentially trim down, but looks reasonable. Let's take a look at a couple of things. So first off, we're going to want to see what our actual performance is like. And so we were doing 30 before, and what we were doing is we're going to want to do we're going to actually want to plug this into a benchmarking framework. So I'm going to do that. We're just going to require that right here. So we have jank.perf already has a benchmarking function in there that builds on top of nanobench. We're just going to use that. So let's run this and let's see how slow things are. So if I run it, this is a really common mistake that people are doing, but and that's just because they're coming from Clojure and how Clojure works. If I run this on its own, well, first off, right now it's not going to work because we don't have jank perf native. Why don't we have jank perf native? Perf native, jank perf native is here. Was that something that we commented out in main? Jank perf native, it is. That should be something that we can have. Let me re-enable this. But what I was going to say is that this is something where people just do they'll just do a jank run, and then they'll do like a time call inside of their Clojure code, and then it'll be like, oh, this is kind of slow, right? And like, sure, jank needs to be optimized. That's what we're doing now. But also, you didn't enable any optimizations, right? And there are a couple of things that we're going to need to do. Jank, to start with, focuses on just like starting up quickly, being able to compile code quickly, and following the C++ nature, defaults to having no optimizations enabled. Like, we compile all of our code at 0. And if you want to change that, then you're going to need to specify some flags. So let's try this again now. Good. So first thing, oh, it's you, the guy who's still coding. My grandfather speak a lot about you. Yeah. These are your grandfather's parentheses. An elegant tool for a more civilized age. Why is this not doing anything here? Or is it actually doing something, but it's just it's just taking a long time? That's possible. It's possible that jank is Yeah, that's possible. Okay, I'm going to assume that this is just so slow. So let's just enable the optimizations that I wanted to enable anyway. Eagerness, eager. I should just change that flag to just be called -- eager. Instead of eagerness lazy and eagerness eager. Because eagerness eager is just too eager. But I think if fib30 wasn't even like finishing there before, let's just change this to like, if this is 10, okay, yeah, then we definitely finish. So 20, we definitely finish. Okay. And it's only 3 milliseconds. So does this just like, but 25, oh, you know what? The perf native is calling into a function called perf. Okay, no, we're already doing, so we're only doing 20 iterations. Okay, so that took 10 seconds. And we're taking 36. I think we just need to be a little more patient because it's not, I mean, it's only taking 36 milliseconds, but the benchmarking framework is running it 30 times. It should only be the 10 warm up and then the 20. Okay. But either way, I'm just going to drop, because I think when we were doing 40, I waited a long fucking time. Let's see, how long did I wait when we were doing this? I waited 20 seconds. I don't want to wait longer than that. So let's jump back to Lion REPL and do the so require criterion and then load file and then quick. So let's just do 25 again here and then get the numbers from this. This actually takes a while as well. So maybe I'm just being too picky. Yeah. I swear we did this earlier and it didn't seem like it took a long time. Okay, so 25, I'm going to change this here to 25 and we're going to do we're going to do these three. So 25, 25. Well, how about that? It's like a millisecond for each one. And 28, Can't read French. Sorry, brother. Okay, so for this, so we are at 36. Yeah. So we'll do these 3608 and 2, 3, 4 jank. So we're not that far off, really. We'll have to see if there's you know, what we can do about this. But we're, you know, it's not like we're 10 times slower. We're not even twice as slow for this one. We'll have to, I don't know if it scales, you know, like maybe jank scaling for this is actually worse. So if we do crank it up, then it's going to be even slower. But okay, so we 36, 15, 18. Yeah. So we're like, I don't know, 30% slow or something like that. If we were to benchmark, no, if we were to profile this, let's try to find out what's actually going on. This is where we get into the goods. An hour and 15 minutes in, we get into the goods. So where is this? Is this the one I want? This is the one I want. I have this handy little note right here for how I'm actually going to run these things. So paste this, and this is what I want to run. Perf. Don't give me that shit. I want perf and hotspot. One thing I love about Nix is just being able to easily get a shell that has something installed, and then as soon as I leave the shell, it's gone. Pfft. Okay, so that is going to give us what we need there. And then we are going to massage the data, and then we are going to massage the data some more. And then we're going to, actually we don't need to do this because we're going to use hotspot. Actually, we didn't even need to do this because we're just going to use hotspot on this data. Yeah, I'm just going to cancel that. Oh, sorry, it's bright. Would be lovely if this used some sort of dark mode, but whatever. Okay, so let's just sort of refresh what we're doing here. So we have a fib function, right? I would expect that the majority of our time is being spent calling fib and then doing plus and doing minus, pretty much. Let's take a look at where we're actually spending our time. So we have a ton of RD refs. And that is, that's something that we could avoid because we don't actually need to be doing var derefs at all. Let's take a look at, okay, so let's take a look at our generated code. This is fun. This is where we're getting into the good stuff. So let me, where was our command? Here's our command. Let me take a look at what our generated code is by taking our command here, and then I'm going to do a jank print IR, and this is going to print our custom IR, and then I'm also going to do a jank print codegen, and this is going to print the generated C++ code that we do, and then it's gonna actually run. I don't care about it actually running. So we get a bunch of C++. And then here is, so this is because we're actually JIT compiling the perf code because we don't have an artifact for that. And so when we do a require right here, so I'm gonna comment this out, and then that's just gonna simplify our output. So then I will do one of these. Cool. And did I just do a, no, I did not. Okay. So this was the IR that we looked at before, where we're grabbing the parameter, we're doing a var deref right here of less than or equal to, we're doing a call on that truthy branch. If we're done, we just grab n and return it. Otherwise, we're going to do our named recursion with -1. We're going to do our named recursion with -2. And then we're going to And then we're going to add those together and return that. So let's take a look at the generated C++ code. So basically, we're going from this these 5 lines here of closure code, and we're generating all of this C++ code. So since this is generated directly in memory for eval, also Johnny, hello, how's it going? I hope you're doing wonderful. Just wanted to stop by and say hi on my way to explaining this, but it's good to see you. The feels okay, man. All right. Well, I hope you're feeling even better in the next few hours. The you got everything. Are you downplaying it, or are you actually just okay? I hope you're great. You're okay? All right. All right, man. That's okay. I appreciate you being here either way. Now, this might seem very odd, where we actually just have some memory addresses here that we're just doing some fucking pointer casting. Like you might look at this and say like, wait, what kind of code gen is going on here? And so this is jank has a couple, like 2 different modes of code gen. One is when we're doing AOT compilation to that's going to be like written out to an object file or a C++ file. And that needs to be standalone. But then we also have this other side of code gen, which is if you're generating code that is just going to be eval directly into the existing JIT runtime of the current process, right? Now, in that case, we already have these objects. So in this case, we're dealing with the number. And if we take a look at the original code, we're dealing with the number 1, the number 2, right? We already have these numbers allocated in memory. And so we just refer to those addresses, right? We just say, yeah, I'm not even going to bother generating the C++ code that's going to redefine this number, reallocate me a number, everything like that. Just take this, the object at this address. It is a boxed integer. And so that's why like all the vars and integers, so we refer to 1 twice, right? Here as well as here. And so that's why you can see this 3b60 and 3b60, that's 1. And then this guy is very clearly 2. And then this var and this var and this var are all different because that is less than equals and minus and plus. So that's what's going on there. But let's take a look. So when we take a look at hotspot, the majority of our time, this is fucking crazy, guys. The majority of our time is being spent dereffing vars. This is 63% of our time. Is that right? No. Let me make sure this is not upside down or something. This is bottom up view. I think it's odd that deref is here, but then add is here. I used to directly inline var pointers in the LOVMIR, and when I wanted to make AOT compilation, I realized I needed dereference module private global vars to initialize it. Yeah. Exactly. Why do we have calls to sub and add inside of the var deref frame? How does that make sense? Because like everything that is above this frame should be things that happen inside of that call. This doesn't look trustworthy to me. This doesn't look trustworthy. Like this makes sense here where var deref is actually next to sub. So in this case, it's like, okay, so we're not spending 63% of our time. We're actually spending 17 or 18% of our time doing a var deref. That seems reasonable. What's going on over here? Eval file, create interpreter. Okay, not stuff that we can deal with right now. This is... Okay, so we see, I'm pointing at the screen as though you, as though you can see. I should really get the like zoom thing that Soding has, but this says aggregated costs in closure core less than equals 411862, and so this is clearly the call to less than equals. That's 6, 7 at the bottom. Come on, Johnny. Come on. Okay, so when we do an add, I'm gonna ignore this guy. When we do an add, we can see that the majority of our time is spent allocating. So we need to allocate numbers when we add them. Similarly, when we do a subtract, we need to allocate the result. And so that makes sense why we're seeing that. Then we're seeing a fair amount of time, 4%, spent just getting jank const nil. Actually, plus this here. So this might be even 10% of our time just getting jank nil. Now, I knew that this is one thing that I expected to see because I know that we have this particular issue. That the way that we're modeling jank nil right now is actually the constant is behind a function. And that's something that we can optimize. It's just because of the way that translation units work in C++, it's annoying. It's annoying because the initialization order across translation units in C++ is not defined. And that ends up biting us since we have globals that rely on jank nil being a thing. So jank nil is not a C++ null pointer. No, it's not. And that's because in closure, dereffing nil is fine. It's well defined, right? You just, like if you do something with nil, you just get an exception generally. But in C++, null pointer, if you deref that, that's undefined behavior. You're no longer within the bounds of a well-defined program. You might crash. You might do anything. It's undefined. And so we can't do that. And so we have to model our own nil. And then that means that we need to have kind of our own pointer type, basically, that can either be nil or can be whatever sort of typed pointer that we're looking at holding. So if it's an integer ref, then it's either nil or it's an integer. And so that's why we have this object ref, integer ref, persistent string ref. Like this whole ref idea is basically Jank's creation of our own pointer types so that we can deal with nil. And then nil is its own object, of course, as well, which does not play well with nominal static typing, and so we need to do some fun bit twiddling to make it so that an integer ref can store nil and also a pointer to an actual boxed integer object. So that's fun. So okay, so we can see here that we're spending quite a bit of time doing derefs, and we're spending quite a bit of time doing this whole nil shit. Let's take a look at the generated C++ code. So when we do our named recursion, what we end up doing here is we grab, the function closure core Fibonacci And then this is just a unique number. And then the final underscore and then a number is the arity. And so our function is arity 1 because it takes in one parameter. And so that's our n here. But every one of these functions takes an implicit sort of this parameter that's named the way that the closure function was originally named here. So this is Fibonacci. And so this is the actual function object that we're having implicitly passed here. Now, when we do our named recursion, we grab this function object, and then we end up doing a call on it. So here's our call right here that we do with, this is the n minus 1. And then here we grab our object again, and we do it right here with the n minus 2. So one of the things I know we can optimize is this whole call mechanism is we're going through the function object, and then this whole dynamic call mechanism. So although we know we're doing a named recursion, we're not actually just calling this C function that we have directly. Like we could just be calling this straight up. Instead of jank runtime dynamic call here, we could just be calling closure core Fibonacci 82358 right here with the same parameters, and it's going to do the same shit, except we're not going to have to do all of the work that we do in dynamic call of trying to figure out if the object that's passed is callable and whether or not it's variadic and how many arguments it takes and everything like that. There's a lot of work that we actually do here. So that's one thing I know we can optimize. Nil in my small implementation is just a null pointer. There are a few checks throw. Yeah, I started that way. And I found that it was really easy to get into undefined behavior land. And I just wanted to rule that possibility out. I don't like undefined behavior. So we could do this, but the thing is that dynamic call is not actually what's showing up very much here. Signed integer addition. Yeah, so for now we inherit all of the C++ behavior for that. The nice thing is that jank is very tightly coupled. Well, nice thing in some ways is that jank is very tightly coupled to Clang. And so that means that we can offer guarantees that C++ cannot offer because we know that we are C++ on Clang, right? And so that means that Clang actually has flags for how to deal with things like Clang args. Yeah, so where is there's a flag, right here, I think. Yeah, so treat signed integer overflow as 2's complement, right? So there's just a flag in Clang that we can pass as part of the Clang JIT runtime, as well as our AOT compilation, everything like that. And this allows us to, even though we're using C++, guarantee that signed integer overflow is not undefined behavior, right? We're not currently doing this, but this is I'm aware of this. I'm just not, I got too much other shit to focus on right now before I start just running through like all of the things that we can do to simplify the semantics of the C++ side of jank. But yeah, this is absolutely something that we can tackle. And there are other examples, I think, where we're going to be able to say, okay, yeah, C++ generally, it can't do this, but because we're relying on Clang, we can. So, I mean, maybe even like tail call optimization or something like that. We'll have to see. We'll have to see. Okay, so we could definitely optimize this, but since dynamical is not showing up here, not too concerned about it just yet. I think that the biggest win is going to be dealing with nil and dealing with the var derefs. Like those, like obviously we need to do the sub. We need to do the add. We need to do the less than equals. We need to allocate for these. For some of them, there's an additional optimization we can do here that we're not going to be able to get done today. But with escape analysis, we can see we can track which arguments are captured by a function, and in this case, n is not captured by Fibonacci. And so when we call Fibonacci here, we know that the output of this is not going to be captured. And so we don't actually need to dynamically allocate the result of this expression. So we could potentially stack allocate this and then just pass in the address of it into this Fibonacci call. Maybe. And I say maybe because we don't know the type of n, which means that we don't know the return type of this subtraction, which means maybe we can't get away with that. But I'll have to explore it. If we can, that would mean that we could avoid a lot of allocations, because we could avoid allocations for each of these for each iteration of Fibonacci. And we would need to allocate for this one because we're returning this. So that would escape. Yeah. So that's one thing I want to explore, and this is the type of stuff that I want to do in jank. But for now, we're tackling the lower hanging fruit. So this optimizing dynamically typed language is so difficult. Yeah, but now that we have the IR in place, I am so fucking excited to get into this stuff. I've been thinking about this for fucking years as I've been building out like all of the C++ interop and jank and everything like that. And I've just been like thinking about the day when I finally get to start doing optimization work. That day is literally today. That day is literally today. So the var derefs, I know we can handle the jank nil stuff. We can optimize that. For the derefs, we have a deref here, we have a deref here, we have a deref here, and a deref here. So that means we have a deref for less than equals, we have a deref for plus, we have a deref for minus. We can get rid of every single one of these. Yeah. We can get rid of every single one of these because the way that Clojure does things, and I know how Clojure JVM is implemented, is that Clojure inlines a lot of these calls. Robin, is your IR in SSA form? Yeah. Yes. This is our IR here. It looks, I mean, it's in Clojure data, which is why it's laid out like this way. But like when you look at these are our blocks right here, and our instructions, everything here is in SSA form. So it's not too dissimilar from like the LLVM-IR that we used to be generating, but it is significantly higher level than LLVM-IR. Like our Jank's IR operates at the level of Clojure semantics, which is, I mean, that's the whole reason why we have a custom IR, is that we already had LOVMIR generation, but LOVMIR generation, like it has LOVMIR has no concept of closure vars and derefs and dynamic calls and our own boxed objects and everything like that. There are just so many optimizations that just not reasonable to do at all. Just not reasonable. And LOVMIR is still there. Like we're generating C++, that C++ will turn into LOVMIR. It'll still be optimized. Like we're still going to get, as much as we can from it, but we have a custom IR on top of that operates at the semantic level that makes sense to us. So that way we can write our own passes on it. So satisfying to optimize your IR and see a better final output appear magically. Yeah, Robin, I was just like talking to my wife about this yesterday during lunch, and I made the analogy of compression. Or like being able to like losslessly compress something where you have all the same data, but you're able to represent it with less data, with a smaller, more efficient encoding, but it gives you the same shit. It's so magical. It's so satisfying. And, so Robin, for your context, 4 weeks ago, we didn't have a custom IR at all. We were doing code gen directly from our AST we had support for code gen from the AST to C++ and AST to LLVMIR. And then, so 4 weeks ago on stream, I started designing and implementing our custom SSA-based IR. And then today, here we are, 4 weeks later, this is ready to be merged into main. So all of our features, AST, everything like that, whole test suite passes, everything is going through the IR. And then we have brand new code gen going from our IR to C++. And so, yeah, today was a big day because it's the culmination of all this work. Now, with that said, we aren't yet doing even a single optimization pass through the IR. But I have been thinking about these, for the past 4 weeks and before that as well. I've just been thinking about all of these fucking optimization passes that we can be doing. And it's very exciting. So yeah, I wanted to get everything just going through the IR first and get all of that merged in. That way I don't spend, more than a month on my own branch doing this stuff. And we're there. But yeah, it's going to feel even more satisfying once we start, as you said, writing some passes and optimizing this IR and doing the same work more efficiently. Love it. Okay, so we can get rid of every single one of these var derefs. So what I was saying was Clojure inlines what it calls inlining. Clojure has its own sort of inlining mechanism that works. It actually works during analysis. And Clojure only does it for some vars, but minus and plus, and I think less than equal, are definitely in that set of vars. And so what happens is these will just be inlined so that there's no var deref at all, and it actually just ends up being so in jank terms, we would just do something like jank runtime add, actually sub, right? So for example, let me, I can manually bring these in. And if we were to, Print. Yeah. If we were to, let's do this one as well. LTE. Does the jank standard library use direct linking? Yeah, so not yet, because we don't. Oh, what the fuck? Look at this, 19? Anyway, sorry. We don't have direct linking written yet, and so no, it doesn't, but it will. This is now that I'm working on optimizations, I get to start doing these things. Okay, so wait. So we were taking 36 milliseconds. Now we're down to 19, which is already faster than Clojure JVM, right? So if we simply inline these calls to just use the native, the underlying native function, we're already faster than Clojure JVM. Now, of course, we need to do the work. We need to do the compiler work to make this happen, right? Maybe we do that. What do you think? Is that the one we do? And of course, that's not where we stop, right? We know that we can still do these nil optimizations, and then we know that we can optimize the code to not do dynamic calls as well. Where was all that? I want to get through all this IR here. Yeah. These dynamic calls for Fibonacci for the named recursion, we know we don't need to do as well. Yeah, let's do this. Let's look into this inlining. I want to see if this is something we can do right now. Because if we're able to do that on stream, then that's gonna allow us to beat Clojure in one fell swoop for this micro benchmark. Of course. In one fell swoop. So the way that works in Clojure, let me jump into projects, third-party Clojure, core.clj, and what we'll have is inline. Yeah, so this is what Clojure does. Clojure, for like something like equal, right? So Clojure has metadata, and metadata for inline is actually just a function. And that function just takes in the arguments and then returns a syntax quoted code. So this is basically like it's like turning the function call into a macro expansion, right? So it's basically saying, yeah, okay, invoke this function instead whenever you call this. And during analysis, whenever you're going to do a var call, we're going to look. So we have inline arities, which is a set of the arities that should be inlined. So basically, whenever you call equals with two arguments, then we're going to just grab this function here. We're going to call that instead, basically macro expansion. And then it's going to expand to this native code, and we're going to replace the expression with this native code. What exactly is dynamic call in jank? That's such an interesting question. I will answer that. But anyway, this is what Clojure inlining is doing. This might surprise you, because this is not like a typical style of inlining. This is a very like manual form of inlining. And you might say, that's odd. Why? Look, and you might even say like, well, look, you can see arity 2 of the function here that takes xy literally does this same thing. Like it just calls Clojure lang util equiv with x and y. Why are we copying this into the metadata? And there's a good answer. There's a good answer that I didn't know until I thought about this for a good long while. Because when I first saw this years ago, when I was first getting into closures internals, I was like, that's stupid. I guess they didn't know how to properly implement inlining. I'm just going to grab it from the body of the function instead. I already have the function source here. But the problem is that the way that closure works with each function being defined in different namespaces, or as Jank calls them, different modules, and the entire program is like not being compiled together statically as like a cohesive unit, you lose the source information for functions that are defined in different namespaces. And by basically duplicating it into the metadata is something that stays with a var. It's something that you can grab from a var at any time. And to put that, an extra function here into the metadata is then to basically allow this code to be used for any var. And that was not as good of an explanation as I wanted it to be. But basically, yeah, the dynamism of closure prevents us from easily doing a typical style inlining. Now, you actually see this in native code as well. This is why we have link time optimization, because if you're compiling native code in two different, so let's say we're doing C or C++, you're compiling native code in two different translation units. You're not going to be able to inline the code between those two functions, assuming that the definition of the function is within the C or C++ file. Now, if the definition of the function is within the header file, because it's a template or it's an inline function, where the definition is in the header, then yes, you can inline that into any translation unit that includes that header. But if it's defined within the C or C++ file for that translation unit, and you call into that function from across translation units, that is also not going to be inlined. And that is why link time optimization exists, because link time optimization takes all of those different translation units, basically object files at that point, and it brings them together, and it builds one big, let's stick with Clang LLVM world. It builds one Clang module out of, or LLVM module, builds one module out of all of those object files, and it has the basically the IR for all of those, and then it starts doing whole program inlining for all of those. But this needs to happen much later in the process, and that comes at a big cost. Since it needs to happen later as well. And so the same could be done with closure, but in order to do it sooner and thus benefit from all of this, not just in AOT world where you grab everything at the end and bring it all together and then try to do your inlining, but to benefit from it in like the interactive REPL programming world as well, the closure devs came up this, their own way of basically turning a normal var call through a var into basically a macro expansion. Okay, that's probably enough explanation there. SatRex75, welcome to the stream. Hope you're doing great. So, let me answer the question, Johnny, about dynamic call. Historically, Jank's objects were not a hierarchy. They were a tagged union. And this was done for performance. I have a blog post that explains all the reasons why. This has changed in the past few years to where we're using inheritance, but again, it's really optimized, and so like it's not your typical type of inheritance. But dynamic call was designed. Dynamic call is something that we can get rid of, and it's something that I'm hoping that on stream, probably, if not on stream, then in between streams, while I'm working on this optimization stuff, it's something that we will get rid of, and we're just going to use call the virtual call function instead. But dynamic call is I think it's in call.cpp. Dynamic call, we have a bunch of these overloads. So the dynamic call takes the source function and then arguments, right? So this one takes no arguments, this one takes one argument, this one takes two, and so on, right? And so its job, so this is the one that takes the source function and then two arguments. Its job is to figure out we have some object ref, which is it's like the equivalent of a Java object. It's a type erased object. We don't know what it is. We don't even know if it's callable. And we need to figure out if it's callable, but we also need to figure out if it's variadic. We need to figure out what arities it supports, and then ultimately how we should grab the arguments that we have and turn them into the shape that the function is expecting. So I'll just take this example of we're doing a dynamic call with two arguments, and we have some function. We have four different cases here. So we have a case where we have a function that just takes args, like so. And so what we do is we grab arg1 and arg2, and we have to create a sequence and then call the function with that sequence. And so this would end up, args is actually here a native array sequence that we create. Then we have the case here where we take one fixed parameter and then a variadic parameter pack. And so I would say it's something like this. And so we would do this and then A2. And so you see here, we'll call source with A1, and then we'll create a sequence and we'll put A2 inside of it. And then we have a case where we take A and B and then arguments. And in that case, this is a ambiguous case where we're passing two arguments, and it takes two arguments, but it also takes this extra shit. And so this ends up being A1 and A2 and then an empty sequence. And then finally, we have the case where we're just going to pass A1 and A2 because there is no variadic argument. So as the number of arguments grows, then we end up with more and more of these cases because we need to scale that. So like if we take a look at here, we're taking 5 arguments, right? Now we need to deal with each of these different cases of like, okay, well, do we put all A1 through A5 into a sequence? Do we put only A2 through A5? Do we only put A5 in a sequence, or do we have A1 through A5 that are all fixed position and then an empty sequence, or are they all just fixed position? And so what we have is we have these arity flags that's actually a bit mask that keeps track of all of this information for us. And I won't explain that, but I will say, if you want an explanation of all of that, then take a look at, I think it's this one. Where is this? I thought it was this. No, but it's not, because this is one I just looked at. Did I not do... No, I did do a... I did... Hold on. Let me... Projects... Jank LAN org... bit... Resources... Source... Blog... Hey, Cypherspace, welcome to the stream. Hope you're doing great. Bindings of VMIR. Optimizing sequences. Huh. I don't actually know where I thought I had a blog post that that explained all of this. I guess I do this for the fast. Maybe I'm just thinking of the fast string where I explain the bits that we're using for Jank string implementation. I guess I don't have an explanation of this. Do I have an explanation of this inside of Callable? No, I don't. All right, well, never mind. Well, I have an explanation of it right here. But yeah, anyway, so we need to answer 3 questions. Is the function variadic? Is there an ambiguous fixed overload? So this is ambiguous here, where if we're calling it with if we're calling it with one parameter and it takes one fixed parameter, but then this one also takes in like a variadic sequence, and then how many fixed arguments are required before we have to start packing. And so anyway, we use a bit set, which is here just a U8, in order to figure out all of this information. And dynamic call handles all of that for us. So this is a lot of work that needs to be done on every single call. And now that we are using, let me just erase all of those changes I made here. Johnny, now that we're using inheritance, we can solve, I think, all of this just using virtual dispatch. But it would mean that we just need to make a custom object for variadic functions as opposed to just fixed argument, like non-variadic functions. And then the dispatch for those will end up doing different things. And I'm hoping that we can just remove dynamic call entirely. Hopefully that answers your question satisfactorily. But yeah, it's some shit, man. There's some heavy shit going on. Okay. My ABI is call fun solve arg crv and the function. Yeah. 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 So I think that we can remove all of that stuff now that we're not using tagged unions and rely on virtual dispatch. The nice thing about that is that's also going to mean that we can rely on some C++ optimizations like devirtualization. So if we have the full type of of whatever callable that we're calling, and then we do a arrow call on it, the compiler is going to know like the function that it can jump to, and can just remove the whole virtual dispatch from that call. But that wasn't showing up in, that wasn't showing up here yet. So we are going to do that optimization, but we're not going to worry about it just yet. I want to take a look at, this. So inline arities, trying to get back to, inlining these things on the AST, because if we can do that, then we know that we can already beat Clojure JVM, which is pretty fucking great. Now, there's one problem here, which is this. Fuck. We may not be ready to do this one yet, because Jank's metadata is not currently evaluated, which means that if you have a metadata, yeah, I wonder what would happen if we did this in Jank. I don't actually know. Oh, yeah. Okay. This is not a good one for us to do right now. It's going to be a great win, but we can't do it yet. We need to add metadata evaluation, and I don't want to do that right now. So inline is literally a list instead of already compile function. Yeah. So in Clojure JVM, this is going to be a literal function. But in Jank right now, we're just going to read this as a list. We could eval the list. We could eval the list. Shouldn't be difficult to eval the metadata. Yeah. I think, well, my main concern is that it expands to like code gen as well. L Kolonk, welcome to the stream. That's, hey, it's really cool to have you, actually. I really enjoy your stream. So shout out you. Thank you for being cool. Hey, LG. Okay, maybe. Oh, dang, Jank is cool. No, you're cool. Let's give it a look. Let's give it a look. So I'm going to search anal proc and get into my analyze processor, and we're gonna do analyze call. Jump into this guy. Okay, so we already have some checks here. If our call is a symbol, oh, now LSP kicks in and jumps me to analyze symbol. Yeah, LSP is so slow in this file because this file is like over 5,000 lines of C++ that brings in a lot of like LOVM Clang headers, and it just takes so long to compile. You need to emit code that would attach the eval metadata AOT compiling, or should that already work somehow? Well, that's the thing. Yeah. So right now when we do code gen, we don't eval metadata either. We just build the data. So yeah, I don't, but we can work around that for now. I want to see what it looks like, and then if we need to just do like a hacky eval, then we could do that and put a to do in there to improve that. Let's see. Okay, so if we have a source, if the source is a symbol, analyze the symbol. If the source is a CPP type, then we're going to do a constructor, CPP value. Okay, and then here's where we do macro expansion. Okay, and now if the source here is a var deref, then we're going to, so we're already doing some metadata shit here. And this is some hacky stuff that I think we're not even actually like supporting anymore. So I'm not concerned about actually ripping all of this out. This is part of the old code gen related stuff that we were doing. But yeah, so if we're in a var deref, then we can check some shit. And we're already doing macro expansion here. So basically we're just going to do something very similar to this. Let's take a look. So I'm going to take, what do we do here? If we say if supports unboxed input, if supports unboxed input, supports unboxed output, then blah 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 blah, needs arc box, blah 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 blah. Okay, I'm gonna remove this stuff for now, and I'm gonna keep this. Okay, metadata, arity meta says, give me the metadata from the var, and I'm doing a get n, so I'm creating a vector with some shit. I don't want to do that. I don't want to do a get n, I just want to do a get, and we're looking at inline arities and inline. So let's just do, hey web dweller, welcome. I hope you are doing great. So I want to do inline arities, and that's going to be a set. I don't need a vector here, so get rid of that. And okay, so this is just going to be inline arities. And then why is there no matching call to get for this? Why don't you like my call to get? To get or not to get? I think it does like I think this is the LSP I was talking about being super fucking slow. So we're not gonna worry about that right now. Inline fun. And so we're just going to do this. Okay, so inline arities should just be a set if it exists. So what we're going to say is if inline arities is sum and runtime do we have a contains? Yes, we do. So inline arities, and then what do we want? We want the current arity. So we have arg count. Bam, right there. So we just going to do a make box for arg count. Cool. I don't even need to do an is sum check, I think, because contains Yeah. So this is just already going to do a nil check. Okay. So if we contain, if inline arities contains the current argument, then grab inline fun, and we're just going to need to say if inline fun is sum, and I want to just actually do a print line. I'm going to do a bing bong of inline fun. Inline fun to code string. Okay. So let me save this, and then let me just do a test file. I don't want to hack this into Clojure Core yet, because Clojure Core just takes a while to compile. So let's just do inline, and then this is going to be just like X, and then we're just going to, let's say, we're going to return, jank runtime inc X, let's say, and this takes X, returns inc X, and then we'll do a let X is 1, and then foo X. And then we need inline arities. Inline arities, which is a set 1. Hey Aslam, I want your opinion about this in C++ roles, not anymore for juniors. Do you recommend me switch to another domain like backend, or taking the risk to stick with C++? By the way, my level is mid C++. DSA, I don't know what DSA means. I think it depends on your industry. Like in game dev, for example, C++ is very much still a thing, and they're going to need junior devs as well. I know that it's tough being a junior dev, but there are industries that are built on C++, and those industries will continue needing junior devs. So if you have invested in C++ already, you know, if you're mid-level in C++, I don't know what mid-level is C++ is for a junior. Like, I mean, are you junior? Are you mid-level? But like, if you've invested years into C++ already, then it probably makes sense to lean into that. But also, like, I don't know your situation, man. I can't tell you what to do with your life, you know? Like, I'd worry too much about, I'm not going to pretend like I know the answer to everything, you know? But to me, it's like C++ is still going very strong. There are a lot of people who need C++. And C++ is one of those things that it really takes a while to learn. And not like learn to the point where you can just write some C++, but like learn to the point where, like, you know C++, you know, you don't just know C++, you know, like, all of the shit that C++ can do to you. That's important, you know? And if you know that stuff, then you're not easy to, you know, you're not that easy to replace. compared to fucking JavaScript or something like that. So the other thing is, it depends on where your interests lie, you know? If you're like, yeah, I dig C++, I like systems programming, I want to work in whatever industry, embedded or gaming or high performance computing or, you know, whatever you're doing C++ with, then, you know, that's important too. I got into gaming because I liked being in gaming, and I was doing C++ because I dig that. Okay, so we're printing this and we actually just have a list. So yeah, we're not evaluating this right here. Let's say. So I'm just going to hack this in. And I'm going to say kind, object kind, type. Is this type? Oh, object type, persistent list. Okay. So if we have a list, then actual fun, then we're going to a runtime eval. Do I have that? No. But I do have a runtime context eval, inline fun. And now let's print this guy. Why isn't there a runtime eval? Yeah, I don't know. There should be. Hey, Elias. Is there any way for jank to interop with Rust? Maybe it would be exact same as with how C++ interacts with Rust. Yeah. It would be the same as the way that C++ interacts with Rust. Jank is C++. Like whole runtime is C++. It compiles to C++. I mean, you can take an entire jank project and just compile it to a set of C++ files, and then you can compile those C++ files, you know, using whatever sort of external tooling you want, if you're so interested in that. So if C++ can interact with Rust in any particular way, I don't actually know the details of how that's done, but it stands to reason that it would work. It would work similarly in jank. Wait, why is that not? So we didn't make it into this because it wasn't a list. Oh, you know, it's probably not a list because it's just a seq. Also, I forgot a comma. It's probably just a sequence. Yeah, I'm probably just being, I mean, this is hacky code anyway. I'm just being a little too defensive. I should just fucking eval this, shouldn't I? Yes, okay, Jay. Eval it. Yeah, I'm just gonna kill that so we can just do this. Yeah, we have an open ticket for evaling metadata, and I think that I had one of my mentees look into it, but it was never done. And then I think he got distracted looking into something else that is higher priority. So it's just, it's been it's been sitting there a while and hasn't been tackled. I didn't think it was necessary for anything until we hit this, and now I'm like, I wish I had that. Am I going to be at Closure Conch 2026? Fuck yeah, Elias. Are you going to be there? I'm hoping to speak at Closure Conch again. I spoke last year. They haven't put up a call for presentations yet. Thinking about it, I just got into Closure about 5 months ago. Cool. You live in Portland? Oh, nice. I'm in Seattle. Wait, is that Portland, Oregon or Portland, Maine? Shout out Maine. Portland, Oregon. Okay. Okay, so here's our actual function. And we see that this logs, this prints is an actual function. Why is every Closure event over the ocean? Johnny, did you go to Heart of Closure? That was in Leuven, Belgium. That was a great conference. Steger, welcome to the channel. Hope you're doing great. You haven't been to any Closure conference? You missed Heart of Closure then. That was a good one. Okay, so we have I gotta step away. I gotta pee break, and then I'll fill my water, and then we have our function, which means that we can basically do a macro expansion of this. We're basically just gonna, instead of calling macro expand, getting our expanded thing and then analyzing it here, we're just going to call our function, and then we're gonna call analyze on that, and then that should be it. It should literally just be like 3 more lines of code, and then this inlining should be working. Am I planning to go to Europe someday for conference preps? Oh yeah, I mean, I was at Heart of Closure. I spoke at Heart of Closure in Belgium. That was 2 years ago. I'm very interested in going to Closure conferences in general, because obviously, like, I'm building my career around jank. I quit my job January last year, and I've been on jank full time, unpaid, aside from sponsorships and grants, which don't pay the bills. So like I'm trying to get jank shipped and trying to build a nonprofit around it. And so drumming up interest, getting people excited, everything like that is really important. Like, and going to conferences is a big part of that. Plus I just really love doing it. So yes, I do want to go to more Closure conferences, and that includes in Europe. Heart of Closure was amazing. If they do another Heart of Closure like next year or this, I mean, maybe even this year, probably not. I would definitely be going, and for any of them, I will be submitting. I'll be submitting talk proposals to not only be able to talk there, but also to get the expenses covered, you know, of flying across the world. All right, give me a couple minutes. I'll be right back. All right, we're back. Let's do this. Let's make it happen. So if we have our actual function and we know that our arg count is within the supported inline arities, all we need to do is call our function. That's going to give us more data, and then we analyze. We just analyze that. So we'll just call it expanded. That's what we already have. So we'll just do a dynamic call with the actual fun. And then we need to give it the parameters as well. So what do we have for our parameters? Ooh, our parameters. So we have a list. Do you sometimes watch Janet or some other Clojure streamer? Yeah, I watch Janet. I don't know of any other Clojure streamers aside from me and Janet. Janet was, and Janet's the OG Clojure streamer. She streams more often and is a much bigger streamer, and is probably more interesting, more entertaining. But if there are others that you know about, then let me know. Okay, so wait, how do we want to grab these args? We have a function, and when we call these, they're unevaluated because they just get quoted in. They're unevaluated. Jen is by far biggest Clojure streamer. Oh yeah. Oh yeah. Okay, so we can't actually do a dynamic call. We have to do an apply to. Apply to. And that's going to take our function, and then it's going to take our args. And our args is, we are just going to, we're going to take our list that we have here. So this is the list of our whole call, and we're just going to, we're going to do a rest on it, and that's going to, so I'll show you. We basically have like a, foo 1, 2, right? And so what we want to get is just the 1, 2, and so we're just going to do a rest on that. Runtime rest of O. Wait, O is a fucking persistent list, right? Yes, it is a persistent list. So what does it have? What does it have that I want? It has a next, probably. Has a next. We'll just do that. That will work just the same for our case. Does that have like a unwrap or something? No? All right, I'm not going to trust that error because it's probably just because it's being slow. Okay, so we take expanded, we return, and then this says expected that. That's probably wrong as well. So let me just save. I think that's it. And then the only thing that's really hacked in here is just this eval. Whereas normally we wouldn't need to eval this because the value that we get for inline fun here would be already evaled. And so we would just probably check here if it's a function. Hope it works. Yeah, me too. All right, let me get rid of this. I'm actually just going to close that. And let's just enable IR printing and CodeGen printing. And then once this is done, so then we'll take a look. Okay, go. Not a number. Okay, so something happened. All right, let me disable this. So we can see here that in our let, we have a let here. Why is the let happening? Oh, let me enable eagerness. Eager. There we go. So here's our foo. So foo takes in x and does an inc on it. And then our let gets brought into a function, and then we grab our var, we deref it, and then we do a dynamic call on that. So this is when we have the metadata disabled. Now, when we enable the metadata, now foo is the same shit, but you'll notice here inside of this guy, we don't grab the var, we don't do a deref, we just do a jank runtime increment of x, right? Yeah, eagerness, still bugging me. So this is good. Like our inlining happened, but what is this error about? Not a number x. I know why. We've done closures inlining. We've hacked it together. Honestly, was not much. This is 13 lines of code. Very nice. So that means that if we were to, and here's the thing, we're going to jump into closure core. Now, I mean, to be fair, like the only hacky thing that we have here is just the explicit call to eval, because it's not, the meta is not eval for us. Everything else here is going to stay. So once we get the evaling of meta, like it's going to be less code. So let's just, maybe I think I'm going to keep this open. I'm going to open up a new terminal. And I'm going to go to jank compiler runtime. I'm going to open up core.jank. And then we're going to jump to def equals. Where's equals? Here's equals. Ay caramba, fun. Welcome to the stream. Okay, so for our use case, and we're just gonna focus on this fib shit for now. So we have less than equals, we have plus, and we have minus, right? Let's do those. Let's do those. So I want less than equals. Where are you? Okay. And then, yeah, we're gonna ignore this for now. So inline arities, inline arities 2. Now what happens when they, so inline arities never does anything for like the other arities. Like they don't inline arity 1, for example. Why not inline arity 1? That seems like a great one to inline as well. I don't know. We're not going to worry about it. Don't get hung up on that. Okay, and then inline. So we're going to have a fun that takes LR, and then we're just going to grab that. We're just going to yoink it. And then we're going to remember to syntax quote J. And then that's that. So that's less than or equal. And then we're going to, I'm just going to yoink that. And then we're going to do plus and minus, max, blah, 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 blah. I think plus and minus are above. Yeah. So we're just going to do this. We're going to do that. And then LTE becomes sub. And then aside from that, nothing here changes. And then plus is this sub becomes add. And then aside from that, nothing here changes. And then we just do a save. Oh, brother. Oh, right. One of the things that we hacked in early on was, early on in the stream, I mean, is that we disabled the compilation of Clojure core again. So I'm going to re-enable that for a brief moment. This call is ambiguous. Oh. What? What? You're ambiguous. Fucker. Okay. Hold on. Let me do... Wait, how? Yeah, so the ambiguous check comes from the C++ side when we're doing function overload resolution, but I don't know why it's doing overload resolution. Yeah, I don't know. So I'm wondering if, was that done for plus 1362? No. Let me jump to 1362. Right here. Yeah, I'm gonna try to replace this with this. Is this right for the list function? Did I get that right? Doc list. Yeah. Unknown implicit conversion from, because that needs to be quoted. Fair. Oh, this one doesn't give me, We're seeing the dark side now. Okay, I'm gonna try to port all of these. Things are getting more and more hacky as we go. Okay, so it should just be those three. Damn, why is this? Why? And also, it wasn't ambiguous when we did it here. What's different? Okay. Okay. I have a new theory. Okay. So it's not to do with the syntax quoting. Sub add. Okay. And then 1363. So here we are. LTE. Why is it ambiguous? We're going to jump into the ambiguous. CPP util. Where is this ambiguous? This call is ambiguous right here. Oh, to do, show all matches. That's what I want. Hey, I borrowed check, by the way. Going to bed. Thanks for hanging out. Good to see you. Nice work. Nice work on those docs today. Thanks. Yeah, so the problem here is that we're getting multiple overload resolutions. I actually think this might be right. I think it's a really bad error, and that's why we have a to-do here. But I think it actually might be correct in terms of the error. Integer, real, object, real, integer, real, object. So we have a bunch of different overloads here. And one thing that would really the thing that would cause this to be ambiguous is if we don't actually have an exact match, but we have an approximate, like we have an indirect match, or rather we have multiple indirect matches. And so what we really want to know is what are the argument types that we're dealing with here. And so let's print those. And I'm going to do that just easily. So we're just going to say for auto const type in arg types, we're just going to do a util print line arg type, and then we're just going to so we have type dot mtype. We're going to do a get qualified type name on that, and we're just going to print that out. But we should only have, so this is for less than equals. N is an object ref and 1 is an integer ref. So this should be object ref, integer ref, which should be this one. This should be the overload that we match. Oh, this is a straight up int? What? Okay. Fascinating. Okay, so here's what is happening. So somebody is using less than or equal to. Yeah, like right here, for example. Probably right here. Probably right here. So this is getting the C++ numeric limits of an I32, and we are doing a less than equals conversion with it, or a less than equal comparison with it, and that is being inlined. And so, oh, okay. What was happening before was, before the inlining, we would see that the right side here is a native value. And in this case, it's a JTL I32, which is effectively an int. And then we would see that the function that we're calling is a closure function that takes in object refs. And then we would automatically do a conversion, because we know that int is convertible to object refs, and so we'll do an automatic conversion to box the integer into an integer ref. But when we inline the call, we're not doing any of that. We're just doing a straight up C++ call, and that C++ call is getting object ref and I32. And we have object ref here and I64. So it's probably ambiguous between object ref I64 and object ref F64, but it's not either of them, because int can become an I64 indirectly, and it can become an F64 indirectly. Yeah, that makes inlining these I think that what we should probably do is a template. We should probably just have a catch-all template. Or maybe even two. So if we do a template, so we have L and R, and then we're just going to say these are const. And so we're just going to say like something like this. Here's a bit of meta programming. So we're going to say if const expression, which is a compile time if, and then we'll do integral is integral. So we'll say if if L is integral, then we're gonna want to static cast it to an I64. But then we want to deal with R. What's the cleanest way to do this? There's a C++ trait for selecting two types, selecting between two types based on a predicate. I'm gonna need to look up what it's called again, because I think it's gonna give us exactly what we want. Conditional. So it should take a condition and then a true and then a false type. Yeah. So what we want is actually, we're going to have an adjusted left. So we're going to have like a, we're going to have a new L that's going to be conditional. And that will be conditional. So if L is integral, then just give me an I64. And otherwise, just give me L. And then we're going to do the same thing for right. And so that will handle integrals. And then we need to do the same thing for, so we'll do IL and then RL. Wait, that's confusing. Int L, real L. Naming's tough. And so here we'll take int L and we'll say if it's floating point, and then L, R, R. And have I lost you all, or is this making sense? Basically, I have these two types, left and right, and I want to do two conversions. I want to say if it's integral, like as in int or char or int16 or int32 or long or whatever, then just give me an I64. Otherwise, just give me, whatever it was. And similarly, if it's floating point, if it's a float, if it's a double, if it's a long double, whatever, give me F64. And so basically we're converting, we're converging all of our integral and floating point types into I64 and F64. And then all we need to do is return LTE with a static cast. And so we're going to do real L, L, and static cast real R and R, and then that's it. So we're gonna, if this works, then we're gonna need to do the same thing for, all of them, probably add and sub and LT and everything like that. That'll be our catch-all. V2DI2N, how is that? V2 Daitun. I have no idea how you pronounce that, but welcome to the stream. I hope you're doing great. Joey 2001, hope you're doing great as well. Welcome to the stream. Okay, so now we're generating the core libraries, which means now we're compiling Clojure core. And so this is where we were hitting that ambiguous overload before. And we made it past. So yeah, we're gonna need to do that for all of the functions that we're doing this inlining for, at least all of the math functions that we're doing the inlining for, to make sure that they can handle any mathy like types, any sort of integer or floating point types that we might throw at it. And that's cool. That's fine. No problem. Okay, so what we've done now, I'm going to close this. What we've done now is we have added this inline and inline arities to less than equals, plus, and minus, which means that we should be able now to jump into, so I'm going to hack this again to no longer fuck with Clojure core since we've changed it. And now we were doing 36 milliseconds. And when we manually modified this, I think we've lost it now to the log. What I remember, when we manually modified the fib, here, when we modified it like this to skip the var derefs, we dropped it down to 19. So if we keep everything in here, and this is saved, this is how this is. When we run this, we should similarly be down to 19. That's what I'm expecting. So let me make sure. Perf 03. Eagerness, eager. We don't actually need perf here. That's only for when we're profiling. 20. So not quite 19, but we did it. So we already beat Clojure JVM. Fuck yeah. Fuck yeah. So the long-term fix here is to do once we're evaluating meta, we can remove this eval. We should check that the value is actually a function. Should we? Nah, we can just apply it. It'll throw if it's not a function when we try to apply it. But yeah, we definitely have a to-do to remove this eval once we can, and then we can update this comment because this was based on the old code that was here. So we can say some vars define meta. Some vars have meta, which defines how calls to it can be inlined. This works similarly to macro expansion in that there's just a function for us to call, which gives us the new form to analyze in place of this form. First try, BCM, thank you. Okay. That was too easy, right? Yeah, we did went into some bad error reporting, like this ambiguous call. Like we don't have good source information on that. We're also not including the like which overloads were matched, what the argument types are. Jank has really nice error reporting in some cases, and has really bad error reporting in other cases. So we also we need to clean up this eval once we can, but we're also going to need to go through each of these functions. So we did LTE, but we're going to need to do LT and mul and div and sub and add. All of these that we're inlining like this, and we're going to need to make sure that they have a catch-all that converts arbitrary native integer and floating point types into the types that we're expecting, so that way we can do proper overload resolution. Oh wait, there isn't 6-7 bottom left anymore. Aw, sorry, Johnny. Sorry, not sorry. $19. Now we can go better. We can go faster. We can do more. Let's see if we can skip the dynamic call altogether. Because if we take a look at the let's jump back to fib here and then print out the code. So now we can see what we have. So we don't have any more var deref. So we don't have any more vars here at all, right? So we just have grab one, and then straight up call to jank runtime less than equal. So this is the inline. And then let's see, we convert that to a bool object and then check if that is true. So like this is wasteful here because we already have a bool in v4, but the way that the IR is written is that we always convert we always want an object, like a boxed object, which then we hand into truthy. Ideally, these two can go away entirely, and we can just use v4 in this if. So that's already an optimization that we can see that we can do. This isn't going to buy us much, but it will certainly buy us some, right? And it is an optimization we're going to do. I don't think it's an optimization we're going to do right now. But then we do our sub for 1. Then we do our named recursion. And then we do our sub for 2. And then we do our named recursion. Let's take a look at how we could optimize this named recursion. Because right now we're just doing a dynamic call. So if we jump into, and also let me make a note here. So jank started at 36, and then after inlining this, and this, we're down to And then I just did, shoot. Run these again, I think. So 19.92. 20.74. And 21. Okay. And then, so I think we can, yeah, we can get rid of, we're not doing this right now. We can get rid of this. And now we can step away from this and then jump into our code gen for named recursion. So named recursion right now is just straight up doing a dynamic call. Yes. Yeah, what I want to know here is, even though I'm a little bit understanding what is Python or C, but what here is going on, I'm not totally sure. That's okay. That's okay. If you have specific questions about what's going on, then I would be happy to answer them. But I mean, what's going on here is pretty advanced, because, you know, not only are we writing some code, but we're writing some code that is affecting a compiler that is then generating some other code. So there are multiple levels here, you know, and that makes it hard to follow sometimes. Makes it hard for me to follow sometimes. So I can get that. But speaking of follows, welcome to the stream. We're writing code that writes code. Pretty much. Yeah, pretty much. Compilers, man. So we want to conditionally do a dynamic call here. And the condition is going to be based on whether or not the function that we're in is variadic, or at least whether or not the arity that we're going to be calling is variadic. So here's named recursion. Okay. Is it based on C? Well, the compiler and runtime is written in C++. So C++ is originally based on C, but these days is a much more complex and robust language than C. But they are certainly similar. Named recursion. Okay, so inside of our named recursion, I want to be able to know if the function that we're that we're recurring into is, or at least that the arity that we're recurring into is variadic. That's what I want to know. And I want to find out I want to find out where I should be finding that out. Is coding still done by hand nowadays, or is it all just prompting and copy pasting? I'm coding by hand and have been for the last 3 hours on stream. I code by hand. Very rarely do I use an LLM to help me with some code, but that's only when I really only use an LLM when I'm doing Clang related stuff and there's no documentation for their API, but there's a lot of existing code. And so LLMs can be helpful for that. But I code by hand. And jank is, well, we could do a get ls files in compiler runtime. Well, let's say in include and source. That's going to give me all of these. Maybe we'll just do CPP. And so yeah, we have about 63,000 lines of code, of C++ code. This is all written by hand. Yeah, exactly. It doesn't matter how good AI gets at writing code. I still want to write code by hand because that's what I enjoy doing. All right. So let's see. I'm in a call here. And here's where I detect that it's named recursion. So I should be able to figure out if this call is variadic, or if this arity is variadic. What is a recursion reference? Yeah, recursion reference gives me a function context, and a function context is going to be able to give me the arity information. Okay. So that means that so we have a recursion reference right here, which is V12, and then we have named recursion on that recursion reference. Recursion reference, all we do here is we use the name. But if we look inside of function context, we're going to have is variadic. We're going to have param count. So this is actually straight into the arity. Is that right? When we get the recursion reference here, find named recursion is just based on the sim. It's not based on the arguments. So what sort of wow, 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 wow. Okay, so here what we're gonna have is the simplest case is we could just check is variadic. That's gonna tell us if there are any variadic arities. And then we could go beyond that to check if this particular arity that we're calling is variadic. Now we have two things. We have the recursion reference, which is just the name of the function, and then we have the actual named recursive call. So the recursion reference is what gives us this Fibonacci here. So Fibonacci is the current function that we're in. This is the recursion reference. And then the named recursion is right now just this dynamic call that goes through the recursion reference. They're separated because sometimes you do a recursive reference without actually calling it. Like you might have a function that just returns itself, for example, which is totally valid. Have you ever seen the cow programming language? I don't know what the creator was thinking. That's what you want to do? I'm not familiar with the cow programming language. Is that a cow programming language? Programming for bovines. Esoteric programming language, humorously with bovine in mind, and words use the word moo as commands. No, that's not that's not what we're doing. I don't think the recursion reference should have this info. It's only the named recursion that should have the info. So we should do one of these. Bool needs dynamic call, which starts at true, let's say. And then what we'll say is, if expr recursion ref function context is variadic, in particular, if it's not variadic, then needs dynamic call is false. Otherwise, if it is variadic, then we have a more interesting case here of expr recursion ref function context function arities. And so what we could do is for auto const arity in arities, and then we'll do that by reference. And arity has a function context and params. So if arity.params.size, if arity param size is equal to arg idents.size, and arity function context is variadic. Ooh, am I able to know if an arity is variadic? I don't think I am. I don't think I'm able to know that right now. I don't think I have that information from analysis. Okay, so then that means that what we have is here a to do, check if this particular arity is variadic. Now in our particular micro benchmark, this isn't gonna matter, but I just wanted to do it. I wanted to do it fully and completely. Closure doesn't allow variadic inlining. Yeah, exactly. Well, so I mean that's why, like, I don't want to do anything fancy if it is variadic, but I don't have a way to check if a particular arity is variadic right now. I can only check if the whole function is has any verities that are variadic. Check if this particular arity is variadic. Needs per arity info. Just spend half an hour trying to do if const expression requires t constructor x, but without t or x being template types, end up having to introduce dummy template class. But you were able to do it. Okay, so named recursion, I'm going to now pass this additional info in called needs dynamic call. And named recursion, bool const needs dynamic call, named recursion, bool const needs dynamic call, and that goes here, needs dynamic call, and then instruction, named recursion, we have bool needs dynamic call. Okay, now inside the CPP processor, what we can say is if instruction needs dynamic call, then go ahead and do this. Otherwise, what we can do is we need to get the name of the current function. And so we don't have that. What do we have inside a builder? Let me mark where we are here. What do we have inside a builder? Block function. We have B function. B function name. Name. Okay. We'll see if all of this comes together. Okay, so this is pretty close, but we forgot to give it the name here. But aside from that, we can see here it's just taking the current function name and calling that, which is great. So let's try this. Good. And now what we need. Why are we not passing the recursion reference in? We were doing that automatically before. But now we're not. Inst fun. This one. This is the one. It works. Watch. Calling it. All right, link. Go. Nice. Cool. So now we don't have the dynamic call. We're just doing a call directly to this. So that removes 2 dynamic calls per iteration. So let's do another benchmark. Maybe it's not a big difference. We'll see. Ooh, 17. I'm going to save that. After removing dynamic call from named recursion, zing. 18. It's definitely like 1 to 2 milliseconds faster though. Because we went as high as 21 before, and we did not now. Now we went as low as 17. Ooh, bought us a couple milliseconds. And a couple milliseconds when you're only dealing with 20 milliseconds is 10%. So that's pretty fucking big, actually. All right, now let's take a look at our code again. So, yeah, we talked about how this bool conversion and truthy can go away entirely. We could just be using v4 directly here. Can't do much about this. This is fine. I wonder if we could change the IR gen so that we don't need to generate locals for these. This isn't going to impact performance though, because the compiler is just going to, like the C++ compiler is just going to remove that. It mainly impacts code size. How is jank even compiled AOT versus just in time? When is it direct? When is it transpiled into C++? I've never asked this question, but I think I haven't figured it out yet. The closure runtime semantics are mind-boggling, Johnny. So in the simplest case, when in the simplest case is just-in-time compilation, which is you're going to run a file or you're going to eval some code from a REPL or whatever. You imagine you take whatever code you're going to run, you generate it into whatever your target code is for code gen. Clojure JVM does JVM bytecode, and we do C++. And then you JIT compile that into machine code that you add into the current process. That's the simplest case. But there are a couple of different variations from that. So there's AOT compilation, and AOT compilation is the same as JIT compilation, but there's more on top of it. So whenever you AOT compile in Clojure, you also JIT compile. This is like a really crucial thing about how Clojure works, is that you can't AOT compile Clojure without also JIT compiling it. AOT compilation is just an additional effect of JIT compiling, where you take like the artifact that you JIT compiled, and then you write it out to the file system. And so Clojure takes all the bytecode that it generated for the JIT compilation, and it writes it out into a class file. And so jank will take the C++ code and write it out into like an object file or a C++ file, depending on what your output target is. Now, we talked about how this code can change depending on AOT versus JIT compilation. So like the fact that they were using an integer ref as just a straight up pointer here to an object that we know exists in memory that is an integer, that we can only do this when we're JIT compiling. Clojure isn't transpiled into Java, no, but Clojure generates JVM bytecode directly. So it's not too different, like Clojure could be generating Java, it wouldn't be very different. But so AOT, in this case where we have this code here, like this only works in the JIT scenario. And so when jank AOT compiles, we actually do C++ code gen twice. We'll do the C++ code gen for JIT compiling, because you have to JIT compile all of the stuff that you're AOT compiling. You need to load it all up into memory. And then we'll do a second pass. And we'll second pass that is specifically for AOT. and the C++ code gen for AOT is tweaked. We're not going to be using references to constants that are in memory. You know, we're going to lift this up into a global instead, and we're going to refer to that. And then there's, I'll answer your question, your follow-up question in a sec, but there's actually another case, Johnny, that makes this interesting, which is that closure is also interpreted sometimes. And so there's this whole eval side of the closure AST, and closure JVM does the same exact thing, where if you have something like a def expression in the AST, and you're evaling it, not AOT compiling it, but you're just evaling it from the REPL or running a file or whatever. For each top level expression that that closure does, it doesn't always just wrap each one in a function and do code gen. It instead interprets as much as it can. And in my first talk that I gave at ClojureConf in 2024, I think, maybe it was 2023, called How to Build a Closure Dialect. I had a section in there about how closure is actually interpreted. And so for a def expression, for example, if you do code gen for that, the code gen for a def expression is like, okay, intern the var, and then create the meta that you need, and then do whatever you like code gen you need for the value, and then bind that as the root of the var, and then set the meta on the var. And like you do code gen, it does all that. But like, because the Clojure compiler is so hooked into the runtime, you don't actually need to do code gen to do any of that. You can just intern the var, like eval whatever value you have, set the meta on the var, and bind the root. And so a lot of the stuff that Clojure ends up doing is not actually code gen. It's just interpreted. So you just mean the jank C++ LLVMIR face. Yeah, so why can I see C++ as a thing isn't jank compiled directly into LLVMIR? Okay, so basically you're asking, why are we generating C++ and not LLVMIR? Right? Well, the answer to that is because of C++ interop. So jank has, like jank on main right now actually has support for generating LLVMIR. But the problem is when you do C++ interop and you're accessing arbitrary C++ members, and you're calling virtual functions, and you're throwing and catching C++ exceptions, and you're dealing with all of these C++ semantics with regard to like references and whatnot. LLVMIR is not for C++. LLVMIR is just like a general native IR. It has no like first class support for these C++ semantics, and thus it has no first class support for the C++ ABI. And so if jank were to do all of this in LLVMIR, including all the C++ interop stuff, we would need to effectively write our own C++ compiler that generates LLVMIR for all of the C++ stuff that we're doing. So yeah, we can know how it's compiled if we want to write a C++ compiler for all of this. But like even the way that functions are called with function call ABIs, like if you give multiple parameters, then it's like, oh, that's on the stack. And but if those parameters are integers, then, then they go into registers. And like there's all of this extra shit that we just don't want to have to worry about. And in C++, it is ridiculously complex. So generating LLVM IR, even when we do that in jank, whenever we're doing any sort of interop, what we end up doing is we generate a bit of C++ code. We generate a C++ helper that we then call into, and it does the stuff for us that we need it to do, and then we go back into IR land. Now, Clojure JVM doesn't need to do this because JVM bytecode has first-class support for everything that Clojure wants to do. But LLVM IR is much lower level than C++, and it doesn't have first-class support for everything that we'd want to do in C++. So if jank is compiled, does it always go through C++, or does it enter the intermediate C++ phase whenever we enter some interop stuff? So yeah, I mean, jank is interpreted as much as Clojure is, and so we try to avoid compilation whenever we can. But whenever we compile, we go to C++. And that's because having multiple code generation, like some in C++ and some in LLVM IR, is like, that's literally what main has right now. And it's something like 12, combined, it's something like 12 or 13,000 lines of C++ to do both of those is too much. And so when I wrote the custom jank IR this past 4 weeks, and then I wrote the new C++ code generation from that custom IR, I did not do LLVM IR, and we're just focusing on C++. The other reason, Johnny, is that when you do C++, you give the opportunity for Clang to optimize that C++. When you do LLVM IR, a lot of that optimization ends up falling on you in terms of generating good IR that LLVM is going to know how to work with. So literally each piece of code first produces C++. Yeah. So I mean, that's what we're looking at right here. We have this function fibonacci, right? So this is a jank function. It turns into this IR. So this is Clojure core Fibonacci. Like we're in the namespace we're in is Clojure core because we haven't actually defined another namespace right now. So Clojure core Fibonacci. We keep track of the lifted vars, lifted constants. And then inside we have a C function that we're going to generate, Clojure core Fibonacci 82412_1. And I said before the _1 is because it's arity 1. And then these are all the instructions that are in there. And then during code gen, we take all these IR instructions and we turn them into C++. Yeah. And the other thing is with Clang, like with generating C++, we get to just focus so much on using auto here and using auto ref for reference collapsing and taking advantage of C++. So in the LLVM IR support that we did, just supporting C++ exceptions. So first off, we need to implement our own C++ exception handling, type dispatch, everything like that. It was several thousand lines of code. It was something, I don't know, like 5,000, maybe 4,000 lines of code. It was so much. And it took the guy who worked on it, Jin Ling, one of my mentees, months. It was like 6 months of work to get like that full exception, C++ exception handling in IR, because we needed to effectively implement the C++ compiler side of exception handling ourselves. And that's just too much. That's not the sort of shit that we should be having to deal with, you know? Like I'm trying to build a novel programming language with unprecedented C++ interop that's also a closure and has competitive performance with Clojure JVM. I don't want to be dealing with like LOVMIR bullshit. It's slower in terms of performance, and it's significantly slower in terms of like maintenance and writing code. The only benefit is that it's faster to compile than C++. That's the only benefit. And I'd rather just like tank the compilation time. Deal with that. Jank is kind of like Clojure script in this aspect. What do you mean? I plan my compiler is to do IR first and then write an interpreter for the IR. The interpreter is then debugger, allows me to also do performance profiling. Only after that will I add. Yeah, that makes sense. That's a good way to do it. Okay, so looking at this, we've removed the dynamic calls here. We've removed the var derefs here. I was saying that like, yeah, we have this and we could potentially clean that up, but it's really not going to impact performance, so I'm not too concerned about it. I think that in terms of optimizing this further, cleaning this up to just use v4 here for the condition would be good. And then that escape analysis we were talking about to potentially avoid the allocation. But in terms of code gen, squeezing any more out of this would be tough. Just a couple things we could do. The rest of it is going to be optimizing the runtime to just make, you know, make sub faster, make allocation faster. Like changing the GC would help here. Oh, and then the jank nil stuff. That's what we were taking a look at. So let's do that. Let's do the perf one more time. We'll take a look at this. 03 eager fib. Yeah, so this guy. And then inject this. And then hotspot. Clojure script produces JS, not WASM. Yeah. So this is not giving us what we want because we didn't actually do this. Cool. So var deref is gone. We see a lot of time being spent here in the GC land. Let's just, can we lock this down to the main thread? I believe I just did that. Yeah. Okay, so this is apparently happening on the main thread. That's interesting. Okay, not too worried about that because I'm not going to worry about the GC right now. But yeah, so we still have this jank nil stuff. And this is potentially like 10% that we could trim off here. Another 10% maybe. So maybe another couple milliseconds we could trim off. Yeah. So I'm going to do this next, but I'm not going to do it now. I'm not going to do it now. For now, I'm good. For now, I'm good. What we've done today is we've gone from 36 down to let's say 18 milliseconds. That is actually half, isn't it? That's actually half. We cut our time in half. Fuck yeah. And that wasn't so bad. It only took these 2 changes. And we know we can squeeze out another 10% from optimizing the jank nil usage here. And we know that we can, where's that? We know we can, like, this is dead code. Like, we don't need this conversion call. We don't need this truthy call. We know we can get rid of that as well. So, like, yeah, we've already cut it in half. We're already faster than Clojure, and we still know we can do better. So that's fucking great. The Huggo 42. Welcome to the stream. Hope you're doing lovely. Hope you are doing lovely. Let's take a look. I got nobody on. I want to send you folks too. But I am going to wrap it up here. Man, what a stream today. You guys have been great. For all of those folks who came in the raid who aren't normally hanging out with me, I do this, generally I just do this every Wednesday. So once a week at the same time, would be great if you guys, drop a follow. Doesn't cost anything. You'll know next time I'm on. Check out Jank. It's not production ready yet, but we're getting there. And as you can see, we're competing with Clojure. In just today, we're already, for this micro benchmark, started out slower. Now we're faster. So I'm going to keep working on optimization for the next few months. And if we can do this in a day, just imagine what we can do in the next few months. Just imagine what we can do. It's going to be fucking great. So I'll catch you guys next time. I hope you have a good one. Adios.